Good evening, Namaskara, Vedantu Karnataka students. This is your Captain Shreyas, and welcome to the KCET 2025 series, also helpful for your PU boards as well as Comet K. And today we are going to go to the next topic, which is lenses and combination. So, ಎಲ್ಲರಿಗೆ ನಮಸ್ಕಾರ ಹೇಗಿದ್ರಲ್ಲ ಎಲ್ಲರೂ welcome. Hello, Mahadev. Nice to see all of you. And quickly let me know in the chat box if I'm audible, visible. Yes, and live. Yes. So, my name is Captain Shreyas. I have been training kids for more than 13 years, and I'm very proud and happy that my students are doing extremely well, no matter where they are. And now it's my turn for all of you to make sure you do well, not in just your PU examination, but also KCT exam. ದಲ್ಲಿ ಚೆನ್ನ ಮಾರ್ಕ್ಸ್ ನಂದೆ ಬೇಕು. Hi, good evening. First PU class for board exam ಮಾಡಿ ಸರ್. ಮಾಡ್ತೀನಿ. Actually, what is happening is I have to focus more on 12th right now because time ಸ್ವಲ್ಪ ಕಮ್ಮಿ ಇದೆ. So you understand, ನಿಂದು seniors ಇದಲ್ವಾ, so they have very little time and they have a lot of expectations. I will definitely take up first few topics also very soon after I do some high weightage topics of 12th. Don't worry. Meanwhile, you keep learning 12th standard topics, okay? We will do 11th standard first PU topics also. So let's begin, and I hope you guys have smashed the like button. If you have forgotten, do that. ಬೇಗ like ಮಾಡಿ, ಬೇಗ subscribe ಮಾಡಿ. Vedantu Karnataka KCET PU Comet K channel. Yep. So let's begin with the concept of refraction at curved surface. We have seen basic refraction before in the first class. If you have forgotten, sir, where is that first class, sir? It is there on the channel. First of all, subscribe. Yes, or else you will miss all the classes. We had done where is it? Refraction at plane surfaces. Okay, this is the lecture which we have done. Total internal reflection, refractive indices, apparent depth, all these concepts we have done there. Hi, Supreme Soul. Good evening. Yes, important questions ಮಾಡ್ತೀನಿ. ಇದು ಸಿಲೆಬಸ್ ಕಂಪ್ಲೀಟ್ ಆಮೇಲೆ ನಾನು ಏನ್ ಮಾಡ್ತೀನಿ ಅಂದ್ರೆ all the important chapters questions, high weightage, then even low weightage important questions, then sure shot questions, mock test question series, PYQ series, all this, yes, portion ಇದು ಕಂಪ್ಲೀಟ್ ಆದ್ಮೇಲೆ ನಾನು ಮಾಡ್ತೀನಿ. All right? Okay. Now, see, when you talk about refraction at a curved surface, what do I mean by that? So let me write it down over here. Refraction at a curved surface. There are many examples of it. Before I give you the theory points of that, what do I mean by refraction at curved surface? Imagine you have a water drop, a drop of water, and maybe there is some dust particle over here. The rays of light will go here like this, and if you see, you can draw a normal over here. It is going from dense to rare, so it will bend away from the normal. So it is refracting at a curved surface. There will be many more such rays which will be refracting like this, and maybe if you extend it somewhere behind, maybe an image will also be formed. This would be the object then. Or take the example of, let's say you have a test tube. Okay, something like a test tube over here, like this. Okay, so this is a test tube. And how will water or any liquid fill into it? It will fill like this. You would have seen this is something like called as the curvature of the meniscus. Yes, there is a meniscus of a liquid, and the liquid will fill like this. So again, curved surface and refraction will happen. So imagine if there was something over here, the rays will go out like this. Then one of the ray will probably denser to rare, so it will probably go out like this. So this is how refraction is happening at a curved surface. Forget that. Imagine taking an example of a lens, a lens, convex lens, or even a concave lens. Doesn't matter. Concave lens or a convex lens. The below one is a concave, this is a convex, vex bulges out. That also has refraction at curved surface. The rays will refract and then it will bend over here like this. The rays over here will bend like this. Maybe they'll go like this, then maybe like this, and then maybe like this. So refraction at curved surface is also happening over here. All these are examples of refraction at curved surface. Is it absolutely clear? Okay. Oh my God, you're doing morning studies at 3 o'clock. Oh, that is too cool. Hats off to you, T channel. That's really cool. Hope everybody derives inspiration. Now that you see the examples of curved surface refraction, even our eyeball is refraction at curved surface. Eyeball is curved, light is entering curved surface, refraction at curved surface. So many examples. So what is the formula to locate where the image is formed? So that formula is what we are going to see quickly, and then we will start solving some questions on that as well. Imagine there is a surface like this. This is curved in this particular manner. Okay, like this. Okay, and maybe the surface on this side is made of different material. So I'll show it like this over here. Maybe this is one medium, this is another medium. It could be air water, or it could be water glass, or it could be diamond air, or it could be air and some glycerin and some diamond. Who knows? Some two different mediums are there. This medium has a refractive index of mu1. This medium has a refractive index of mu2. Let's say the object has been placed over here. This is where your object has been placed. So then from here to here is basically the object distance, where this becomes the curved surface's center becomes your pole, and obviously a line which is passing and dividing the surfaces equally passing through the center, that becomes your principal axis. That becomes your principal axis, isn't it? Maybe the rays will refract somehow or the other, and maybe the rays will go like this, who knows, and they will meet here. Example, maybe there will be more rays also like this, but to form an image you at least need two rays. Maybe there is an image which is formed over here. It could be real in this case. If it is formed here, it would be virtual. This will be then the image distance. Standard notation like in mirrors, u is for object distance, always measured from the pole. V is for the image distance, again measured from the pole itself. Is that clear? All distances are measured from the poles, and you have to use sign convention. You have to obviously use sign convention. Without sign convention things won't work. So what happens is the formula goes as follows. You first take the second medium where the refracted rays are, and then put below it the image distance, and then from that subtract the first medium's refractive index, which is mu1, and divide it with the object distance. That's where the first medium is. That will be equal to, use the same order, mu2 and mu1. So mu2 minus mu1. And then finally what you need is one last thing, and that is basically this curved surface, right? It will also have some radius. It will also definitely have some radius, definitely. And maybe this is the center of curvature. So you have to put the radius of curvature over here. So this becomes the formula to locate the image given the refractive indices, object's location, and the radius of curvature. So it's an important formula, my dear students. Is this absolutely clear? This formula? Everybody with me on this? Okay, let's see an example based out of this. Maybe we can open up some previous year question maybe somewhere over here. Yes, we have a question. Okay, this is a proper KCET question. A luminous point object, it is over here. It is at a distance of 2r from the pole. This is a curved surface. This is a medium of refractive index 4 by 3. This side is a medium of refractive index 3 by 2. Two different mediums. Radius of curvature of the surface is r. And question is, the image is obtained at what distance from the pole? Okay, let's try to understand who is what. This guy is obviously the first refractive index, because that's where the rays from this particular object will come, like this. So this is the incident light. This is where the incident light is. That means wherever the incident light goes, that side will become positive and the exact opposite side will become negative. Correct? Sign convention, guys. So this will be positive. Obviously, this will be the negative side. Okay. Object distance also we know. So what will be the object distance u? Object distance will be negative. It will be negative 2r. What about the radius of curvature? Radius of curvature is on the positive side because the center is on the positive side. So r will be plus r. Image distance, we do not know. And lastly, obviously, this thing over here, this refractive index will just become mu2. Okay. So mu1, mu2, r, u, v is unknown. So use the formula. Mu2 by v minus mu1 by u is mu2 minus mu1 divided by r. What is refractive index of the second surface, second medium? It is basically 3 by 2. Image distance unknown. What is refractive index of the first medium? 4 by 3. What is the object distance? It is basically negative 2r is equal to mu2 minus mu1. That means 3 by 2 minus 4 by 3 divided by radius of curvature, which is basically r. Perfect. Let's see what happens next. Let's solve it step by step. 3 by 2v. Okay. Now here what I will do, this is 3 by 2 minus 4 by 3. We'll take the LCM. The LCM of 2 and 3, that is 6. So 3 multiplied by 3, 9. 4 multiplied by 2, 8. And obviously this r remains. Minus minus is plus. Take it on the other side, it will become negative. So it will become 4 and 2 cancel. So it will become 2 and then 3 r over here. But if you want to leave it as it is, if you are getting confused, no issues. We can keep 4. 3 2s are 6, so 6r. The good thing is the denominator is the same, so we can subtract easily. 9 minus 8 is 1. 1 minus 4 is basically 3 with negative sign divided by 6r, and we have 3 divided by 2v over here. Now 2 and 6 cancels, 3 and 3 cancels, so 1 by v is equal to negative 1 by 2 goes with 6 3 times, so 3r. So therefore, what will be v? V will be nothing but negative 3 times of r. V will be negative 3 times of r. That's it. I think the answer given options here are slightly wrong. Okay, because r is not mentioned if I'm not wrong over here. Yeah, so basically it is 3r unless r was given to be 10 centimeters. Is r given to be 10 centimeters somewhere? Oh yes, r is given to be 10 centimeters. Perfect. So if r is 10 centimeters, so answer is 30 centimeters. Perfect. So r was 10 centimeters. So definitely it will be minus 30 centimeters. Minus means the image will be formed here, and this is having a refractive index. You can see 1.33. This is 1.5. So technically this is the rarer medium. So the image, the final image will be formed somewhere over here. The final image will be formed somewhere over here at a distance of 30 centimeters, at a distance of 30 centimeters here, and this is formed in the rarer medium. Hence this option, yes, it is correct because r value was given. Yeah, I hope this is absolutely clear. Yes, this is more than enough for KCET. KCET won't be asked anything beyond this. Yeah, this is in fact even enough for JEE and NEET sometimes. So KCET in front of it, definitely it is going to be more than enough. All right. So I hope you understood how refraction at curved surface works. Now let's go to the next application of refraction of curved surface, which is called as lenses, which is basically called as lenses. So when we talk about a lens, when we talk about when we talk about a lens, observe this carefully. You have a curved surface, you have another curved surface, and maybe this is the principal axis, maybe this is the principal axis, maybe the ray of light might just come like this, and at that exact location, if you draw a normal, maybe it's going from rare to dense, so maybe it will bend towards the normal, maybe like this. And again, let's say we end up drawing another normal right over here. Okay, another normal right over here. So again, it will bend over here. Maybe it's going from dense to rare, so it will bend away from normal, and it will go like this. So you can see the refraction is happening at two surfaces. So that is basically a lens. A lens is nothing but refraction at two surfaces. Refraction at two surfaces. Now, what we study in our syllabus is something called as refraction at two surfaces, that is a lens, but a thin lens. That is what we will basically end up studying. So a thin lens, when you have, usually our lenses will be thin lens, then what happens is, for this surface, this is the pole 1. For this second surface, this is the pole number 2. For the lens as a whole, this is the center of the lens, which I will call it P. For a thin lens, the thickness is so less. The thickness is basically less. Because of that, P1 approximately equals P2. All these 3 points are the same thing. That means all distances are measured. All distances are measured from P, and it won't affect the calculations. It won't affect the calculations at all. So that is the advantage of using a thin lens. If imagine this is 2 millimeters, this is 5 meters. 5 meters, 2 millimeters, 2 millimeters is negligible. So whether I measure from here or here won't matter. Even if I measure from here won't matter, because the lens is basically thin. So when I say thin lens, it will be something like this. This is a thin lens. So this point, and this point virtually are the same thing. So this is basically a thin lens. As you can see, it's got a very small width. It's got a very small width. I hope this is absolutely clear. Everyone understood till this point? Very good. Awesomeness. Shall we move ahead to the next? Now you will be like, sir, if a lens is nothing but refraction at two surfaces, so wouldn't you technically use this formula 2 times to see where the ray goes and meets? Exactly. We will use this formula 2 times for this surface and this surface, because this is basically surface 1. This is technically your surface number 1. And this is technically your surface number 2. So we'll have to use the refraction curved surface formula 2 times. But don't you think it is a headache? What if I tell you it is already derived and we know the formula? What happens when you get it, when you use it 2 times, the refraction at curved surface? Hi, Dr. Tanuja. Nice to see you. Thank you for the blue hearts. So what happens is, when you use that formula 2 times, you can directly locate the image. It becomes easy. So we define few points before we go ahead. First of all, this type of a lens, then this type of a lens, then this type of a lens, and then, oops, this type of a lens. What are each or type of lenses called? This is basically a convex lens. This is a plano-convex lens. Plano-convex lens. This is obviously a concave lens. This is a plane surface with a concave side. So plano concave lens. So that's how the naming goes. If you further bifurcate over here, all these lenses on this side, they are basically converging in nature, whereas this is diverging in nature. And the reason for that, you can see how the rays of light will go once they enter the lens. Like for these lenses, when the rays of light will enter over here, you will see they will converge at a particular point. Same thing over here as well. Maybe they converge over here somewhere like this. Whereas for these kind of lenses, you will see these rays of light, they will diverge like this. They will end up diverging. That's why they are called as diverging lens. That's why they are called as diverging lens. In fact, you can see where they diverge from by extending those lines behind. You have to extend these lines behind to see where exactly do they diverge from. The point from which they end up diverging or converging, the point from which they exactly diverge or converge, here they converge at this point, here they converge at this point, that is called as the focal point. So is nothing but F is nothing but the focal point. So if rays of parallel beam of light is incident on a lens, wherever they meet, that is the point of focal point. Yes, that's exactly the point of focus, and it might actually end up meeting or appear to diverge, appear to meet if you extend it backwards. Either ways, it is the focal point, correct? Everyone clear till this point what is the meaning of focal point? Next important thing is the focal length. Yes, this distance small f, this distance small f is called as the focal length. This is basically called as the focal length of that particular lens. And we can see probably some simulations if we have. Right now, this is a convex lens. If I place the object really far, you can probably see how the almost a parallel beam, if you neglect this part, it's almost like a parallel beam, how it is converging over here. If I use a concave lens, you can see how almost a parallel beam, the rays are diverging from this point. So this is the focal point for a concave lens. Are you able to see that, my dear students? Parallel beam, almost the rays are diverging for a concave lens. For convex, they end up meeting over here. So that's how it is. This is absolutely clear, everyone? Beautiful simulation. Now you might be wondering, sir, can you please tell me the focal length? Yes, definitely. Why not? There is a formula for this particular focal length. Let's have a look at it. So if you have this as the first surface, this as the second surface, it could be equal, it could be not equal. Who knows, right? So I'm just chumma showing random to unequal surfaces. And let's say this is the radius of curvature of the first surface. Let's say this is the radius of curvature of the second surface. So this is something like this. Okay. C2, this is C1. This radius obviously will be R2. This radius will obviously be R1. The actual pole will be here. This is the pole. Now, if the parallel beam of light is coming from here, they will end up meeting somewhere here, let's say. They will end up meeting, let's say, over here. Example is showing. Okay, so this particular point becomes the focal point, and from here to here, this is this is obviously your focal length. This is obviously your focal length. This is parallel beam which is incident. This is just to figure out where the focus will be. Okay, did you understand why this is C1 and why this is C2? Lot of times students make a mistake. They call this as C1, this as C2 because they feel this is first and this is next. No, the first surface center of curvature might come on this side, depending on which type of lens it is. It could be a concave, convex, any kind of lens. This is applicable. So even for concave lens, you can see how it will look like. So this is one surface. This is, let's say, another surface, and this is obviously your principal axis. Then uh, this would be one radius, this would be probably another radius. In that case, the first surface center, this is the second surface's center, so that is C2, and obviously the pole will be somewhere over here. And needless to say, this will be R1 and this will be R2. Now obviously we have to define who is positive side and who is negative side. Incident light is going this way, so that side will be positive. So this is the positive side, of course, and the exact opposite side will be the negative side. So this is obviously the negative side for our sign convention. So we have this formula for finding where the focus is, what is the focal length. That is why we call it as the lens maker's formula. Lens maker's formula, because you can find the focal length based on what the refractive index is, what the radius of curvature is, and all these things. So that will give me what is the focal length. That's why lens maker, to make the lens of a particular focal length, if you tell me the parameters, I can tell you what focal length you will get. That's why lens maker formula. How do you get this formula? It is derived using mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r two times for two surfaces. So it is derived using that formula, first for this surface, then for this surface, shifting the sign convention and all of that. And what is the answer that you get? Here is what you get. The answer for the focal length is as follows. 1 by f is equal to the relative refractive index. This is always relative to the outside one. So the relative refractive index minus 1 into 1 by R1, the first surface radius, minus 1 by R2, which is the second surface radius of curvature. So that is what you basically end up getting. So this is the lens maker formula. If you're wondering what this mu relative is, it is the refractive index. It is the refractive index of the lens with respect to the outside medium. With respect to outside medium, yes. So that means technically it should be refractive index of the lens upon refractive index of the outside medium. If it is water or some glycerine or some other liquid, kerosene, whatever, so you have to take the relative refractive index. The focal point will adjust and change accordingly. That's very, very important. Yes, Mandar, my UPS went berserk and it gave up. It shorted. I immediately called the electrician. It's sorted now. It's sorted. And that's the reason why on NEET English, Baswa sir had to take over. Luckily, I thought I will have to cancel my Karnataka class. So luckily, everything got sorted before time. Okay. I'm so glad, Pradeep. And I will be no problem, even if you're watching the recorded classes. And I know some of you might not be able to, or some of you prefer recorded. No issues. No issues. No issues. There is nothing wrong in watching recorded classes. There is absolutely no rule that you have to watch live. The only thing why I insist on live is some students sometimes, you know, uh, don't get that motivation to watch recorded, or sometimes lose interest in recorded, or you will postpone, I'll watch it tomorrow, day after. So that's why if you have that procrastination attitude, so live classes are better. Otherwise, if you are self-disciplined and you can concentrate, recorded classes any day will also be the same output. Yeah. Yes, Mandar, all teachers are teaching from the home. Yep, except for Gopika ma'am. Yep. All right. So coming back to the point, we saw what is the formula. Now using the focal length, I can find everything else about the lengths, and we'll come to that one by one. First of all, talking about the power of a lens. Power of a lens is nothing but the power, how powerful a lens is the degree of, not the degrees of angle, the degree of convergence or divergence. Convergence or basically divergence. And the sign convention goes as follows. If the power is positive, that means it is a converging kind of a lens. And if it is negative, if the power is negative, then it is a diverging kind of a lens. Also, the magnitude of the power, the magnitude of the power, the magnitude of the power is directly proportional to that degree, to the degree of convergence or divergence. Now, if you take the example of a convex lens and then a concave lens, you will notice that as you make a parallel beam of light fall onto them individually, for a convex lens, obviously it converges. For a concave lens, it obviously diverges. So you have to extend it behind to exactly locate where the focal point is. Now, if you notice over here, the focal length for a concave lens in general will be negative. For a convex lens, the focal length will be positive because it is on this side, the focal point. Here, the focal point is on the incident side. So this is the negative side. This is the positive side by sign convention. Now, what do we know? Power should be positive if it is converging. So this is converging in nature. Can you see? This is definitely converging in nature. So the power should be positive. Focal length is also positive. Okay, number one. Number two, if focal point is closer, it is more converging. If focal length is large, then it is not able to converge easily. So focal length is inversely proportional to the power, correct? Hence, the answer goes as follows. Observe this. The power of a lens is 1 by f. If f is positive, power is also positive. If focal length is negative, like you can see, it is then diverging in nature, then the power automatically will come out to be negative. If f is small, if f is small, it will diverge more. If f is large, it will diverge less as expected. So that's why this is the formula for power. And if you ask me what is the unit, sir? Well, you can see the unit of power. In fact, the SI unit of power, it is meter inverse, and that is called as a diopter. Diopter, which is basically meter inverse. Diopter, a diopter is a meter inverse. That's the SI unit of power. Is this absolutely clear? Everybody with me? Perfecto. Now, I'll show you some examples, don't worry. The last point which I want to make over here is, imagine you have a lens. Imagine you have a lens like this, okay? And let's say you have kept an object over here. This is where the image is. This is your object distance. This is your image distance, and want to locate where the image will be formed. So the formulas are as follows. These are called as your lens formulas. Your lens formulas, my dear students. It goes as follows. Do you remember mirror formula? Mirror formula used to be 1 by V plus 1 by U is equal to 1 by F. Instead of plus, you put a minus, that becomes a lens formula. Do you remember the magnification formula, which was the height of the image upon height of the object? Yes, that image magnification formula. If the image is magnified, diminished, inverted, erect, given by the magnification formula. Remember, it was negative V by U. Here, put it as plus V by U. That's the difference, guys. So it is very, very similar, but also slightly different. That's all. That's the only catch in the lens formula versus the mirror formula. Sign difference. Instead of 1 by V plus 1 by U, it is 1 by V minus 1 by U. And instead of negative V by U, it is plus V by U for magnification. Everything else is the same. Shall we now do some questions based out of this? Okay, I hope these formulas are in your head. What is the lens? It's nothing but refraction at two surfaces, but we consider thin lenses. All distances are measured from this point, so it doesn't make a difference. Second important thing, there are many kinds of lenses: converging, diverging, concave lens, plano-concave, convex, plano-convex, right? And you can find the focal length of such a lens using a lens maker's formula, which is ready-made for you. But the mu inside is the relative refractive index. R1, R2 are the radius of curvature by the sign convention of the surfaces. And using that focal length, you can find the power and figure out how converging or diverging it is. You can also find where the image is and how much magnified it is. All right. So I think it's a good time we start with some questions maybe over here. All right. Let's do this. Let's do this particular question. All right, everyone. See, if the refractive index of air to glass's refractive index is 1.5, which is 3 by 2, and water's is 1.33, which is 4 by 3, ratio of the focal length of a glass lens in water and in air. Glass lens in water and in air. Okay. Let's think. First of all, do I know the focal lengths formula? Yes. 1 by f is the relative refractive index minus 1. 1 by r1 minus 1 by r2. Now you consider the following two cases, my dear students. First time, the lens is in basically air. Second time, second time it is in air, and the first time that same lens is in water. The same lens is basically in water. So out of all the things that you have in the lens maker formula, what will change and what will not change? Can you put it up in the chat box? Can you quickly put it up in the chat box? Out of all the things that you have in the lens maker formula, what will change and what will not change? The lens surface will never change. That means this particular thing will remain the same, but this definitely will change. This definitely will change, which means 1 by f1 by 1 by f2. Who is 1? Who is 2? This is the first situation. This is the second situation. First time in water, second time is in air. Okay. Will be technically equal to this mu first time is refractive index of glass with respect to water minus 1. Second time it is just the refractive index of glass with respect to air. So that's it. So there is air over here. That's it. That's what it will look like. So 1 by f1, 1 by f2. So I think f2, this particular f2 will go on the top, right? And this was basically f1, that f1 will go below. Perfecto. And what do we have over here is equal to this. Relative refractive index of glass with respect to water. It is nothing but refractive index of glass by refractive index of water. How did I get this formula? If you recollect, 1 mu 2 is nothing but mu 2 by mu 1. This comes on the top, this goes below. So this comes on the top, this goes below. Exactly. So this -1, and this is just refractive index of glass. That's all, which is standard. You don't have to measure it with respect to air. With respect to vacuum, it's the same thing. Vacuum, air, roughly similar kinds of medium. So what do I get finally over here on this side and on this side? Let's try to figure it out, my dear warriors. Come on. So on the top we have F2 and below we still have F1. So refractive index of glass is 3 by 2, 3 by 2, and of water is 4 by 3. Okay, so 3 by 2 by 4 by 3 minus 1. For glass, it is just 3 by 2 minus 1 over here, right? This is just 3 by 2 minus 1 over here. So let's see what happens in the next step. F2 by F1 is equal to, well, 3 3s are 9, 3 3s are 9, 2 4s are 8, 9 by 8 minus 1, whole thing divided by 3 by 2 minus 1. So I can write it as just 3 by 2 minus 1 like this. Or now in the next step, 8 goes on the top. So 9 minus 8 divided by 8 divided by 3 minus 2 divided by 2, which will then become 9 minus 8 is 1 and 3 minus 2 is also 1. Now this just becomes 1 by 8 and 2 by 1. 2 goes with 8 and 4 times. So 1 by 4 will be F2 by F1. Therefore, what will be F1 by F2? F1 by F2 will be nothing but 4 by 1. 4 by 1 is option number D. So yes, that is the correct answer. That's how you solve this particular question. Thank you, Sandhya. I hope everybody has understood this particular question, how to solve this. Step by step, I have shown you proper KCET kind of questions. Moving on to the next question on your screen. Equiconvex lens is there, made of some refractive index, focal length f in air. If it is submerged in water of some refractive index, what is the change in the focal length? Okay, let's try to understand it. A lens made of glass has a focal length of f in air. So if you talk about the focal length in air, it is f. Refractive index of glass is 3 by 2. There will be some R1 and R2. So I will not touch it because it will anyways remain the same, just like in the previous example. No matter where you immerse it, this will not change. So I'm only worried mainly about this particular term over here. Next time, what happens? It is immersed in water of some refractive index. Don't you see? It's a very similar problem. It is now relative refractive index of glass with respect to water, guys. And this is again 1 by R1 minus 1 by R2. You just now have to divide both of them and you will get the answer. So 1 by F2 is below, and here you will have mu G by mu W minus 1 in the bottom, and here on the top you have 1 by F, and here you have 3 by 2 minus 1. This and this will anyways cancel because they are going to be the same. They are just going to be the same. So this by this, and this is nothing but mu G by mu W. Solve this and you will again get the answer, guys. So F2 will go on the top, and here we will have is equal to and denominator, and F will go over here. 3 by 2 minus 1, 1.5 minus 1 is half. So it is basically just half over here. This one over here, you can just check it out. Glass's refractive index, how much it is? It is given. It is 3 by 2. By water's refractive index is 4 by 3 minus 1. That's it. Now you just have to solve it. So F2 by F is equal to half by 3 3s are 9, 4 2s are 8 minus 1, which is half by 9 minus 8 is 1 by 8. Yes, 9 minus 1 is 9 minus 8 is 1, and 8 remains as it is. So this will become 1 by 2 and 8 by 1, which is just 4. So F2 will become 4 times of the old focal length. So what is the increase? Yes, What will be the increase? It will be 300%. Many of you would have said 400%. Wrong. Understand why it is not 400, it is 300. The question is the percentage change. Read the question carefully. The percentage change. So the percentage change means how much did it change by 4f and f, that is the change. Original f multiplied by 100. So FFF cancels 4 minus 1 into 100, which is 3 into 100, which is 300%. Yes, that is the answer. A lot of people make this common mistake and put as 400% instead of 300%. Got it? Beautiful question again from KCT. Right. So let's solve another question coming up on your screen. The radius of curvature of a converging lens are in the ratio of 1:2. The focal length is 6 and refractive index is 1.5. Then the radii of curvature are. Beautiful question. So it's a converging lens. Let's draw it so that we don't mess up the sign convention. 1:2. 1 is double. Okay. Okay. So I'm just going to be very slow with this question. All right. And this is one radius of curvature. This is another radius of curvature. Remember, this will be C2. This will be C1. If this is R, this is 2R. Why? Ratio of the radius is 1:2. This is 1 meter, the other is 2 meter, 1 centimeter, 2 centimeter, R centimeters, 2R centimeters. No issues, Sandhya. We will, I will keep that in mind. Okay. Now, obviously, by convention, this side will be the positive side and this side will be the negative side. Reason being, our incident light will be coming like this, and whatever is the direction of incidence, that side of the lens or mirror becomes positive wherever the direction is. So it's that side. Arrow mark is that way. Okay, perfect. Let's use the formula. 1 by f is mu minus 1 by r1 minus 1 by r2. What's the focal length? Focal length is already given to be 6 centimeters. So 1 by 6 is equal to, refractive index is already given to be 1.5 minus 1. What's the radius of curvature? R1. See, this is the center one. So this should be R1. So R1 is technically R and it is also positive. Why? Because it is on this side. Can you see? Next, observe carefully. Minus 1 by R2. This is center 2, so this is R2, so that is basically 2R. But do you see center 2 is on the negative side? So that's why this will be minus. So you need to be very, very careful with the signs. Yes. Pradeep, these are taken from KCT, question bank that we have at Vedantu. It's not like from any specific book or anything. We have a question bank and our Vedantu platform itself. So from there, there is a team which makes some questions. They will pick up the questions, I handpick them, and that's how it is done. Yeah. If I had taken it from some book, I would have no issues telling you that book. In fact, I would be very happy. I mean, it's not like I'm keeping the source very secret or anything, nothing. In fact, if you want to make me to make a video, sir, which book should we practice questions from? Don't worry, I'll make a separate video on it, on the best material, whichever team has handpicked the questions from. No issues, Pradeep. All right. So what will happen next? This will become 1 by 6 is equal to 1.5 minus 1 is 0.5. 0.5 means half. Correct? 0.5 means half. This is 1 by r. Minus minus becomes plus. So 1 by 2r. Okay. Do you understand? Or if you want, I'll put one step over here. This is 0.5. So 1 by 6 is equal to 0.5 is half. Okay. LCM. 1 plus 1 by 2 is 3 by 2. So this will become 3 by 2r. Okay. Now what will happen next is just have to move this around a little bit. Yep, r goes on the top. Yep, 6 and 3. 6 multiplied by 3 and 2 multiplied by 2, which is 6 goes with this 2, 3 times. So 3 3s are 9, 9 by 2, which is basically 4.5 centimeters. So therefore, 2r will be 2 multiplied by 4.5, which is 9 centimeters. Hence, the correct answer to this question is 9 centimeter and 4.5 centimeter. So hence, that is option number D. Perfect. Awesome. Cool. Clear. Understood? Oh, yes, sir. Understood, sir. Perfect, sir. You are teaching very nicely, sir. Okay. Sir, I saw one question somewhere, sir. And you know what happened, sir, over there? Okay. What happened, dear? Sir, I saw one flat surface, sir, and it was like this, sir. Sir, I didn't know how to solve that question. And they told, sir, this is 20 centimeter or something. And this was, let's say, refractive index of 1.6 or something like that. Sir, how do I find the focal length of such a thing, sir? Okay, how do I find the focal length? Plano concave, plano convex. No issues, my dear. In such cases, see, this becomes your first surface. This becomes your second surface. Reason? Light parallel beam will come from here. This is the direction of the incident light. That means this side will obviously become positive, and this side, sir, yes, that will become negative. Okay, sir. What next, sir? See, if this is a second surface, that means R2 will be, it's on the positive side. You can see this is the second center. So will be positive 20 centimeters. ಇದು ಏನ್ ಮಾಡ್ತೀನಿ ಸರ್, ಇದು ಫ್ಲಾಟ್ ಸರ್ಫೇಸ್ ಇದಾರ? ಹೌದಾ? ಎಸ್, ಫ್ಲಾಟ್ ಸರ್ಫೇಸ್ಗೆ ರೇಡಿಯಸ್ ಆಫ್ ಕರ್ವೇಚರ್, ರೇಡಿಯಸ್ ಆಫ್ ಕರ್ವೇಚರ್, yes, is what? If it's curved, this is the radius. Less curved, this is the radius. Even less curved, big radius. Almost flat, even big radius. Completely flat, infinite radius. Yes, a flat surface has infinite radius of curvature. That's very, very important. Remember this. Because more curved it is, the radius is small. The flatter it becomes, radius becomes large. And infinite radius for a flat surface. Oh, sir, it is simple, sir. 1 by f is equal to mu is 1.6 minus 1, 1 by r1, 1 by infinity, sir. Okay, this is 20 positive. 1.6 minus 1.6. Okay. What is this 1 by infinity? 1 by very large number, very chintu mintu number. 0 is equal to minus 1 by 20. Oh, what is 0.6? 6 by 10. Okay, put 6 by 10 over here. And this is 1 by 20 over here. Cancel agate 6, and this is becoming 10. So this will become 3 by 100. So 1 by f is equal to 3 by 100. So therefore, f is equal to 100 by 3, which is 33.3 centimeters. Yes, that is the answer. Simple, understood, clear. How to find the focal length? Sir, idu power calculate ಹೇಗೆ ಮಾಡ್ತೀನಿ? Oh, no issues. Power, right? Power formula ಏನಿದೆ? 1 by f. 1 by f. But f has to be in meters. Oh. So focal length, I can't use 100 by 3. 100 by 3 is in centimeters, divided by 100 to convert it into meters. 100 cancel. 100 cancel. 1 by 1 by 3. So it will become 3 diopters. So the power is 3D. Don't say 3D as in 3 dimension. No, it is 3 diopters. That's how you calculate the power. Clear? Understood? Perfect. So that's how you solve plano surfaces. Okay, perfect. All right. Now the next question is, calculate the focal length of a reading glass of a person if his least distance of vision is 75 centimeters. Okay. This is one Pandu. Okay. And this Pandu, what happens is, he is not able to see anything which is very close. In fact, for him, If the distances are below 75 centimeters, he can't see it. So this is often called as the near point for that person. Here he can see, here he can't see. That is the meaning of the word near point, and this is also called as the least distance of distinct vision for that person. But ideally, the least distance of distinct vision for any adult average person is not 75. Ideally, it should have been only this much, 25 centimeters. This is what the ideal should have been. He cannot see here, but he can see anything here. So there is a problem, which means imagine a beautiful girl is over here. One beautiful girl is over here. This Pandu can't see that beautiful girl. Why? Because she is below 75 centimeters. And if that beautiful girl comes very close to Pandu, imagine 25 centimeters, this beautiful girl is coming. 25 centimeters, Ishta, that's it. Okay. He will still not be able to see. So what will Pandu have to do? Corrective measures. He will have to use a lens. He will have to use a, yes, spectacle. And then he will be able to see the Champa. So that means if Champa is over here, this beautiful girl comes till here, he should be able to see. So Champa is our object. The image will be formed over here. See what the lens is doing. The Champa is here, but the lens will push that image of Champa here so that Pandu can see. Champa doesn't know that. That is the trick of that lens. Only Pandu and the lens know it. So the lens makes the image over here so that, because Pandu can see till here, right? So that is the trick which your glasses do. Is that clear? So what is the formula that we will use? Obviously, lens maker formula. So what is our lens maker formula? Sorry, not lens maker, lens formula. 1 by V minus 1 by U is equal to 1 by F. What is image distance? Image is 75. Okay. But which side is positive, which side is negative? You can see the light will go like this. This is the incident light. So this side will be obviously positive side. This side will be obviously negative side. So image distance technically is negative 75 minus object distance is also negative 25 is equal to 1 by F, minus minus plus. So 1 by 25 minus 1 by 75 is 1 by F. LCM is 75. 75, 25 goes 3 times, minus 1 is 1 by F. 3 minus 1, 2. So 2 by, 2 by 75 is equal to 1 by F. Reverse flip it. So F will be 70. So 75. 75 divided by 2, which is how much? Yep, 37.2 centimeters. So he will need a focal length of 75.2 centimeters because it is positive. That means it will be a convex lens. Which lens will it be? Convex lens. So if Pandu uses convex lens, he will be able to see the Champa. Yesterday I attended the test. Which test, Vimla? You're talking about? You mean on the NEET channel, the NEET Ekalavya? Oh, the scores that will come later on. I mean, it is not revealed so easily. It is going to come and the team will get in touch with you. Don't worry. Because they will evaluate and everything. Yeah, answer is 37.5 centimeters. Perfect, perfect. Let's have a look at the next question. This is one of the very nice questions. Let me tell you that the size of the image of an object which is at infinity as formed by a convex lens of focal length 30 centimeters is 2 centimeters. Okay, so there is a convex lens, focal length is 30, the image is formed at 2 centimeters. Okay, so the image is basically formed over here at a distance of 2 centimeters. All right, perfect. Now, if a concave lens of focal length 20 is placed between the convex lens and the image, this is the image, and a concave lens is placed in between at a distance of 20, and the image is at a distance from the lens. Wait a minute. If a concave lens of focal length 20 centimeters is placed between the convex lens and the image at a distance of 26 centimeters or from the lens, a distance of 26 centimeters. This is 2 centimeters. Something is wrong. Okay, we'll just take it over here. 26 centimeters from the lens. This is 26 centimeters, no issue. Fine. Okay, and the image is at a distance of 26 between the, oh, sorry, my bad. I read it wrongly. If a concave lens of focal length 20 centimeters is placed between the convex lens and the image at a distance, and the image is formed at a distance, my bad. So you are just placing this over here, and the image is formed at a distance of 26 centimeters from the particular lens. So from this, the image is formed at 26 centimeters right over here. This is where the final image is formed. Now, why would this be happening? Is because the moment you place a concave lens, it is diverging in nature. So the rays, instead of meeting over here, what will happen is that they will now diverge and they will meet over here. So what happens is, actually, this image is for the convex lens become will become an object for the concave lens. Yes, the rays were supposed to meet there. So wherever they were supposed to meet, that point will now become the object for the concave lens, and where the rays actually end up meeting, that will become the final image location. That is what the thing is. Is this absolutely clear, my dear warriors? Very, very interesting trick which is involved over here. Okay, now it is also mentioned that okay, the new size of the image will be how much. Now where is the concave lens exactly placed in placed between the convex lens and the image? That has not been mentioned, so I'm little bit doubtful over here. I'm little bit doubtful over here if everything has been mentioned or not. So we will do one thing. We will take up this question separately later on, because I feel something is missing over here. This distance is not given. So, just let's give it a halt. Okay, so let's not do that. Now, in fact, this brings us to another interesting concept. What to do? We'll do a similar question. When there are multiple lenses, what to do in such cases? Multiple lenses. See, imagine you have a lens over here and a lens over here, then maybe, I don't know, some random lenses are there, one after the other, many could be there, and you have an object over here. What you will do is, to find where the final image will be formed, the image of a lens becomes the object for the next lens. Use this concept. The image of a lens becomes the object for the next lens, and repeat this process. Repeat this process into the number of lenses times whatever lenses are there. Then you will get where the final image is. Then you will basically get where the final image is. What do I mean by that? There was a very nice question which was asked in many competitive exams like this. You have one convex lens and you have one concave lens. This guy's focal length, let's say 40 centimeters. This guy's focal length, let's say 30 centimeters. It is given to you that a parallel beam of light is falling here, and it emerges also parallelly. And the question was, can you figure out What's the distance between these two lenses? Can you figure out what's the distance between these two lenses? A parallel beam of light falls here and it emerges out also parallelly. It's a combination of lens question and we have to figure out the distance between the two lenses. I'll tell you, you don't even have to use lens formula multiple times. Just have to think in terms of ray diagram. See, when will the ray from a concave lens be parallel? See, it will only happen in one particular scenario. Imagine the rays, just imagine like this, forget this for now. If the rays from this convex lens were meeting somewhere over here, imagine, okay, they were meeting somewhere over here. And of course, from here to here, from here to here, this is 40 centimeters because that's the focal length. But because this concave lens came in between, it will not let the rays converge. It's a diverging lens. So those converging rays, they try to diverge and end up becoming parallel. So imagine this has to go parallel like this. This has to go parallel like this. Eventually, yes, a parallel beam of light again became parallel because, this was the focal point for the concave lens and it eventually became parallel. So now, technically speaking, this is the focal length for the concave lens. That means this is 30 centimeters. Yeah. So this much is 40, this much is 30. How much will this be? Obviously, the answer will be 10 centimeters. And that's how you solve this kind of question. Loved it? All right, Savitri. Fine. Request noted. Awesome. Awesome. Now, usually you might not get these kind of problems. Multiple lenses placed at some distances where you have to make the image of one guy object for the next. Most of the times what happens is you will see this. You will have thin lens in contact. Thin lens in basically contact. And when that happens, that means you have very, very thin lenses, maybe like this, like this, like this. These are thin lenses in contact, each having focal length f1, f2, like that, fn. All these lenses can be converted into a single lens of a new focal length, effective length. And in fact, even an effective power, these powers might be P1, P2, P3, P4, like that, Pn. What's the formula for that? The formula goes as like this. The powers always get added. So the effective power is just P1 plus P2 like that till the nth power, or 1 by effective focal length is 1 by f1 plus 1 by f2 like that till the nth focal length. So this is what you will do when you have multiple thin lenses in contact, 2, 3, 4, 5, etc. Powers add, but focal length reciprocals will add. One of the most famous questions on this is this one. Let's take an example. Let's take an example. If the focal length of one lens is, let's say, 20 centimeters and focal length of other is minus 40 centimeters, can you find out what the effective power is? That's the question. So let's try to solve this. Because we have to find the effective power, that means we need individual powers. That is one way to do it. Or you can find effective focal length and then convert it into power effectively. So what I can do is 1 by f effective is 1 by f1 plus 1 by f2. First focal length is 20. Next focal length is minus 40. LCM is obviously 40. So this will become 2 times. This is just 1 time. 2 minus 1 is minus 1. 2 minus 1 is just 1 by 40. So basically your focal length will become 40 centimeters, which is 0.4 meters. But we want power, not focal length. So effective power is 1 by F effective, So it will be 1 by 0.4. 0.4 is 4 by 10, which is 5 by 2, which is 2.5 diopters. So the answer for that is 2.5 diopters. Is it clear how to solve these kind of questions on effective focal length or effective power? Another question which you might get, and which is very common, is where they will tell you, listen, there is a lens like this, and I have broken it into two halves like this and like this. This original length, focal length was f, and then second time I broke it like this and like this. Can you figure out the focal length of each of these parts in either case? Well, breaking of a lens. Now what will you do? Let me tell you. First of all, imagine if the rays were coming like this and they were finally, let's say, meeting over here. How does it matter whether I take the upper part or the lower part? Still, whatever rays are there, they will refract exactly the same way and they will still meet at the exact same point. This will have no difference on the focal point. Yep, it will still meet right over here. So there is no change in this case. So if the focal length, obviously if it is f, this will also be f. So there is no change in this case. In fact, the intensity of the light will reduce, that's all. Intensity of the light will definitely reduce. Light will be less intense because lesser rays of light are going. That's the only difference in the first case. But for this, here, think of it this way. In fact, if I add these two lenses, I should get this lens. Combination of two lenses to get you one single lens. So the power of the original lens is power of each part, P1 plus P1. If this is P1, this is also P1. This had a power of P, example. So basically each part has power P1. So 2P1 is basically P. The original power will be 1 by f, and this will be 2 into 1 by f1. Each part will be f1 and f1, right, focal length wise. So what will you get the focal length f1 as? 2 multiplied by this f. Yes, the focal length will double. A lot of people think focal length will become half, it will get divided. No, in fact it is the exact opposite, it will become double. The power will become half. Is this clear? That's one common silly mistake which many students end up doing. So that is what we had to discuss today. Lenses, curved surface refraction, combination of lenses, and their questions typically how they are. So we have done with that theory. So we'll take up one more class so that we can complete the entire of ray optics, and that is prisms. So we will do that in the next coming lecture. All right. I hope you enjoyed and learned a lot. And if you did, make sure you like, subscribe, talk about this channel with all your friends, and leave a comment below on what you want next. Okay. So thank you for liking, thank you for subscribing, thank you for sharing and commenting. Bye bye. Take care.